Hello everyone, I am Dr. Alok Kumar Ghoshal, Professor, Department of Chemical Engineering, Indian Institute of Technology, Guwahati. I will be discussing on the course heat transfer. Before entering into the course, I would like to give you the course outline, and the course is mainly divided into several aspects. It discusses the fundamental concepts of various modes of heat transfer, and then it takes care of the different theories associated with it. It develops or shows how the theories have been developed, and it applies to the solutions of practical and relevant chemical engineering problems. Now, some aspects of the process design principles of the various heat transfer equipment are also discussed in the course. This course highlights the concept of thermal boundary layer and boundary layer heat transfer. It also, though the course is primarily designed to meet the requirement of chemical engineers, particularly the undergraduate chemical engineers, it also will be useful for practicing engineers to refresh with fundamental and technical informations. Therefore, the course has got the contents accordingly, and we can see that the course content has starting from introduction to conductive, convective and radiation heat transfer, steady and unsteady state conduction in one dimension, forced and free convection heat transfer analysis for boundary layer flows, condensation, boiling, evaporation, which are very important unit operations phenomena for chemical engineers to learn about. And then there are some aspects of radiation which are being discussed in the form of black and gray body radiation heat transfer with radiation network and radiation shield. Now, I would like to say that you can go through certain text or references. There are several books are available for undergraduate heat transfer curriculum. Some of the commonly referred books are the book of Hallman, J.P. Hallman, heat transfer, it's a Tata McGraw-Hill publication. Then Professor B.K. Datta, heat transfer principles and applications from Prentice Hall, and then D.Q. Kern, the process heat transfer from Tata McGraw-Hill, McEwen Smith and Harriet, that unit operations is chemical engineering, that is also a McGraw-Hill publication. So, these are the references also can be discussed with while studying this course. Now, to enter into the course, the very first thing that comes to our mind is what is this heat transfer and why we should study this course. Now, when we say that what is this heat transfer, the first point is that this heat transfer explains us how and which mechanism is involved and how and at what rate the heat energy is transferred between material bodies. This transport takes place due to the presence of temperature difference, which is the driving force for this heat transfer. So, for any transport to occur, whether it is a momentum transport or heat transport or mass transport, there should be some kind of driving forces. So, in case of heat transfer, there is a driving force, and this driving force is the thermal potential difference, which is nothing but temperature difference, and thermal potential is nothing but measured in terms of temperature. And this transport takes place by various means. These means are normally the conduction, convection and radiation are the basic three modes of heat transfer. We will be entering into these things little later in details. Now, these mechanisms and the corresponding principles, what we learn through the course of these heat transfer studies, with the help of those we are able to calculate the rate of heat transfer from one body to the other and also the extent of transport of thermal energy, that is from one body to the other. As a consequence, we can find out that variation of temperature and heat transfer rate with time. So, this is the need for any process engineers to know how heat is transferred from one place to the other and what is the mode and what happens at different locations at different times, how the temperature, what is the temperature history with respect to time and with respect to place or coordinate. Now, the very commonly asked questions is that what is the difference between this heat transfer and thermodynamics then? Thermodynamics, we know that it also discusses about that heat transfer. Now, I would like to tell you that briefly I will explain the difference. Thermodynamics usually deals with the systems at equilibrium and it is used to find out the amount of thermal energy that is needed for changing a system from one equilibrium state to another. And therefore, thermodynamics does not tell anything about the history of heat transfer rate or temperature while changing from one equilibrium to another between material bodies. So, it says from one equilibrium state to the another, but it never says what is happening in between in the path. So, therefore, thermodynamics analysis is different from heat transfer analysis. In this heat transfer, we will be discussing that how and at what rate the heat is transferred even though there is no existence of equilibrium. Then the question comes, what is the relevance of studying the heat transfer? Why the undergraduate student should study this heat transfer? Now, very importantly, I should say that almost all industrial processes are involved with heating or cooling operations that require heat transfer. You consider any unit operation starting with distillation or any heat exchangers or distillation, absorption or many other cases where you may require to preheat a stream. When you go for preheating a steam, that time you have to heat the raw input or the entry stream, influent stream with the help of some hot fluid, and this is nothing but called heating, and you have to use and heat exchanger for that. So, you need to know that heating operation here, you need to know the heat transfer mechanism for this particular kind of instrument. So, that heating or cooling operation, they require some kind of instrument and you may require to have the knowledge of mechanism of heat transfer in these instruments that is being happening or the equipment that is being happening. Similarly, consider the case of a furnace. You have a furnace where you are heating or you are doing some kind of burning. So, what is happening that the temperature of the furnace walls are very high. What you have to do? You have to see that the energy is not getting lost with the help of transportation of energy through the walls of the furnace, and for that what you have to do? You have to put some kind of insulation on the walls, and you must know that what kind of insulation has to be put, what kind of transport mechanism is involved in that kind of situations. Similarly, you consider the case of storage of cryogenic materials. For example, liquid nitrogen, you know that it is being used in many places, many applications it has. So, if you have to store the liquid nitrogen which is at a very low temperature, and then what is a possibility storing of liquid nitrogen, there can be in leak from the atmospheric temperature into the storage vessel. So, what kind of insulation that you should apply for that. So, all these almost all industrial processes, therefore, they have involvement with heat transfer, heating or cooling. So, that is why the heat transfer study is very much necessary. Now, a chemical engineer with sound knowledge and understanding in principles and mechanisms and applications of heat transfer finds him better placed in a chemical process industry, because when you are working in a chemical process industry, you are given lot of responsibilities that to run the system until and unless you know how and what way the things happens, you are in a difficult situations to have to control or to take care of the smooth running of the units. Therefore, heat transfer has become an integral part of the chemical engineering curricula, and almost in all chemical engineering disciplines that heat transfer is the main core course that is being placed for the undergraduate studies. It is also relevant to mechanical engineers who also do lot of heat transfer studies. Okay, now, to start with, let us see that what are the basic modes of heat transfer. As we told that the basic modes of heat transfer are conduction, convection and radiation. Now, conduction takes place in a solid or a stagnant liquid or a gaseous medium, and this happening due to existence of temperature difference, which is nothing but the driving force. And this conduction phenomena is not associated with the movement and displacement of the particles of the medium from their original positions. And during this conduction phenomena, heat energy is transferred from one molecule to the adjacent molecules through usually molecular vibrations or drift of free electrons. This is in case of solid materials, like molecular vibration in case of general solids, then drift of free electrons, that is in case of metals, and then collisions in case of liquids and gases, etc. And but in all the cases, there is no change in the positions of the molecules from its original positions. Now, typical example of conduction phenomena is the mode of heat loss or gain through the walls. Now, I will be discussing here some aspects of the conduction phenomena through a diagram, and you know that the very basic law of heat transfer is given by particularly by conduction is given by Fourier's law. It is given by Joseph Fourier. It is called a phenomenological law. This is based on the observations that Fourier had for heat transfer through a solid body. So, in this case, you consider that for the case of a typical solid body, let us consider so typical solid body. So, say at any distance x, you consider that this is the dx amount and heat is being say transported in this direction. Let us call that rate of heat transport is qx dot, is the heat transport rate per unit area, and this is at x, and this is, you can say that q dot x plus dx. So, small q dot x plus dx will say that it is heat transfer rate per unit area, and this is happening at point x and this is happening at point x plus dx. And that according to the Fourier's law, that heat transfer rate per unit area, which is nothing but the heat flux, this is proportional to the temperature gradient. So, I will write that heat transfer rate say Q dot X per unit area by area, this is proportional to the temperature gradient del T by del X. So, del T by del X is the temperature gradient along x direction. Then we can say that Q dot X equals to some constant k into area into del T by del X, and a negative sign is put over here. That means, Q dot X is equal to minus K A del T by del X. Now, K is called the proportionality constant, and it is also called, K is also called thermal conductivity. It is the property of the material through which the heat is being transported, and the negative sign, this is very important thing. The negative sign indicates that if you see that del T by del X is the temperature gradient. Now, del T by del X temperature gradient means the difference in temperature by the difference in the distance. Now, difference in temperature is, if we say that T 2 is the final temperature and T 1 is the initial temperature. So, we can say that d T is equal to T 2 minus T 1. So, difference in temperature is always final minus initial, but actually if the heat is to be transported along x direction, positive x direction, if it is to be transported, then T 1 has to be greater than T 2. This is by the second law of thermodynamics, that heat cannot be transported from the lower temperature to the higher temperature. So, heat has to be transported from higher temperature to the lower temperature, and under that situation dt is becoming negative. Dt is becoming negative, but we know that Q dot X is in the direction of x, positive x, and that is positive. So, to make Q dot X, that is that heat transfer rate to be positive along x direction, another negative sign is being added to this. Now, this K is called thermal conductivity, and its unit is in SI unit. K's unit is K is equal to watt per meter per Kelvin. So, K is expressed as watt per meter per Kelvin. This K, this thermal conductivity, is a property of a material. Now, if this K value changes with position of the material, then we will say that the material is anisotropic. And if the thermal conductivity of the material does not change with position, then we call it to be isotropic material. Most of the situations we will assume that the material is isotropic and K does not change with the positions of the material. A typical example, if I say in case of say wood, the wood grains, they are aligned in one particular direction. So, along that direction the thermal conductivity will be sometimes something, and if you see the transverse direction of the wood grains, then thermal conductivity will be a little different. So, there can be a variation in the thermal conductivities, like the case of your fiber, polymer, fiber nanocomposites or composites. You can consider that fibers are reinforced in the polymers, the fibers are aligned in certain direction within the polymer matrix. So, if you consider the thermal properties like thermal conductivity, there can be a variation in the direction of the fibers and in the transverse direction of the fibers. So, however, these variations in general we try to neglect for simplicity, but this K can be a property or function of temperature. So, with increase in temperature K can change. Now, the variations of temperature K for solids or liquids or gases with temperature have got a different kind of variations, because it mostly depends on the kind of conduction mechanism that is involved in gases, liquids and the solids. In general, it is assumed that K is a linear function of temperature or a quadratic nonlinear function of temperature, like that. Sometimes K is assumed that K is equal to K naught into say 1 plus A t, which is a linear function, or K is equal to K naught into 1 plus A t plus B t square. So, depending upon situations, sometimes K is assumed like that as a function of temperature, where A and B are some constants. K naught you can understand for absolute 0, K is equal to K naught. So, K naught is the thermal conductivity of that material at absolute 0 condition. Now, here from the above relations, we may try to define thermal conductivity. We can write K as Q dot X by area into minus del T by del X. Now, when the area is equal to 1, del T by del X equal to 1, then K is equal to Q dot X. That means, K equals to Q dot X when A is equal to 1 and del T by del X is equal to 1. What does it mean? It means that K is the rate of heat transfer through an area of 1 or unit area when the temperature difference or the temperature gradient is unity. So, K is indirectly a measure of rate of heat transport that is taking place per unit area when the temperature gradient is maintained unity. Now, we can understand that K is very high, particularly for the metals, and it is very low for gases and non-metals. So, now we will see that different mechanisms that is being taking place during the conduction phenomena. When we consider the conduction in gas, we can say that conduction in gas consists of usually takes place due to the collisions between molecules of varying temperature. So, one molecule of at higher temperature, it collides with another molecule of lower temperature and then exchanges the energy. So, it is related to the kinetic theory of the gases, and as we know that with increase in temperature, the kinetic energy increases and the molecules movement increases, it becomes faster. Similarly, transport of energy by the conduction process also becomes faster with increase in temperature, and thermal conductivity of the gases are almost independent of pressure up till a moderate temperature. Now, if you go and increase the temperature, then maybe at around critical temperature where or above, where the gas becomes like a vapor and the non-ideal conditions come into picture, at that time it becomes a function of pressure. Thermal conductivity becomes function of pressure. Now, if I say the typical gas, say hydrogen, hydrogen has the highest thermal conductivity among the gases, and its value is 0.175 watt per meter per Kelvin at 0 degree centigrade. As because we have told that thermal conductivity, it could be a function of temperature, it may be a weak function, it may be a strong function, but when we say about the thermal conductivity, we should tell about the temperature, at what temperature we are telling about the thermal conductivity. Now, when we consider the conduction of the liquid, it is similar to the gaseous conditions, but more complicated compared to gaseous conditions. In case of liquids, materials or the molecules also do collide, but at the same time here that another molecular field, force field, that is also applied, because the molecules are close packed. So, the effect of the surrounding molecules and their forces do play a strong role in finding out that thermal conductivity of the liquids. However, the thermal conductivity of the liquids has got a different kind of behaviors. For example, water, in case of water, thermal conductivity increases up to a certain temperature. For glycerin and benzene, the thermal conductivity decreases with increase in temperature. Some of the liquids like light oil and freon, thermal conductivity is found to be more or less constant. And among the liquids, other than the liquid metals, because liquid metals, as you know, that mercury is a liquid metal and it has got a very high thermal conductivity. So, among the liquids other than the liquid metals, water has been found to have the highest K values, which is around 0.63 watt per meter per Kelvin at ambient condition, at ambient temperature something around 25-30 degrees centigrade. And thermal conductivity of the liquid is almost independent of the pressure. Now, come to the thermal conductivity of the solids. When we say that in case of solid, the thermal energy is usually transported by two means. One is called due to vibration, lattice vibrations, and another is the transport by energy transport by free electrons, that already we have discussed. Now, free electrons, transport by free electrons is dominant in case of metals. Therefore, good electrical conductors are almost all are good thermal conductors. Typical examples of these metals you can understand: copper, aluminum, silver, iron, etc. So, they are good thermal conductors, they are also good electrical conductors. At the same time, so any material which is a poor electrical conductor is also supposed to be a poor thermal conductor. There is one exception, and this exception is your graphite, diamond. You know that diamond is an electrical insulator, but it has got very high thermal conductivity, and which is 5 times as good as high as copper or silver metals. Now, it is also found that the solids have also some kind of variations, that is not that the unique variations of thermal conductivity with temperature. For example, copper is being found to, copper, carbon steel are found to have decreased thermal conductivity with increased temperature, whereas aluminum and 18-8 stainless steel, 18% chromium, 8% nickel stainless steel, their thermal conductivity increases with increase in temperature. And thermal conductivity is also decreases for the metals with increasing amount of the impurity associated with it. Because thermal conductivity is one useful information that one should have, because depending upon that information, we would be interested to place the materials in the form of refractory linings, in the form of insulating materials and all. Now, we see that solids with low thermal conductivities are called insulators. These are all thermal insulators. For example, you know the ceramic materials, diatomaceous earth and expanded polymer foams like polyurethane, and you know that this is of low thermal conductivity because of the entrapped air into the pores of the expanded foam. And we know that air is a very poor thermal conductor. In some cases, super insulators are being placed, particularly for cryogenic conditions where we have to take a due measure about that loss of energy, thermal energy. And in that case, multiple layers of highly reflective materials separated by insulating spacers that is being placed, and the whole system is made evacuated This evacuation is to minimize the air content within this system, and minimizing the air content means you are minimizing the chances of conduction between the collision or chances of conduction or collisions amongst the air particles, air molecules. Now, typical values for this kind of super insulators, K value is around 0.3 milliwatt per meter per Kelvin. This is for some feeling, some understanding how much it happens. Now, there is one thing that we should talk about is that refractory materials. These are different from the insulating materials. Many a times people get confused that maybe the refractory materials and the insulating materials are the same thing. It is not. Refractory materials are those, for example, the silica, magnesite, alumina, they should have high thermal or temperature withstandability, and then high chemical resistance they should have. But it is not necessary that refractory materials will be having a low thermal conductivity, but it is desirable. If a refractory material has a low thermal conductivity, it is desirable. Therefore, a furnace, which is a very common example of some chemical engineering instruments or equipment, a furnace is typically layered by refractory bricks, then insulating bricks, and then ordinary bricks. So, refractory bricks is the inner layer where it has got very high temperature withstandability and it has got a chemical resistance. So, that is put at the inner layer of the furnace, and then you have the insulating material. So, that the heat does not get transported in a faster way through the insulating material. So, to the ambient. So, insulating material is putting a lot of resistance for that, and then you have that outer layer which could be some ordinary bricks. Okay. Now, here through this slide I just wanted to show you that typical values of thermal conductivities of various materials at 0 degree centigrade. You can see that the metals have very high values, whereas that including the mercury is also there. Mercury is a metal, but it is a liquid state, it is not solid, and its value is 8.21 watt per meter per Kelvin and watt per meter per Kelvin at 0 degree centigrade. And for the non-metals, we can see diamond, it is 2300 watt per meter per Kelvin, whereas you can see that glass wool and sawdust, they have very poor values, and therefore, many a times that we have seen glass wool, sawdust, they are used as insulating materials. And for the liquids, we have different liquids, you can see water, ammonia, freon, lubricating oils, and then in the gases, hydrogen is the highest 0.175 watt per meter per Kelvin, and carbon dioxide it is very low 0.01146 watt per meter per second. This is some idea that one should have the ranges of thermal conductivity values for the metals, for the gases, for the liquids, and for non-metals, and one can see that diamond is far apart in terms of thermal conductivity. Now, come to convection. So, we have got some idea about the conduction. Now, we will see that convection is another mechanism of heat transport. Now, in case of convection, heat energy is transferred from higher temperature region to the lower temperature region through the displacement of the particles of the medium. As we have seen in case of conduction, there is no displacement of the materials. Here, there will be displacement of the particles. Thus, the convective heat transfer is associated with the displacement of the fluid element, and depending upon the type of displacement, it is divided into forced convection and free convection. When you say that forced convection heat transfer means you are applying some kind of velocity into the fluid element for it to move from one place to the other place by applying some external energy onto it, and this external energy you can apply with the help of some pump or some blower like that. Whereas, in case of natural convection, these molecules are getting displaced for the particularly this kind of natural convection or forced convection phenomena happens for liquid and gaseous or vapor substances. So, in case of natural convection, the molecules gets or fluid element gets displaced from one position to the other position due to the density differences, and this density difference happens or comes out due to the differences in temperatures at different locations of the fluid. So, suppose you are heating a water pool, you are heating water and below you have a hot plate. You have seen that that heating coil that is used to heat water in a bucket. So, what is happening that heating coil, that surface of the coil becomes hot, and then because of that immediate adjacent molecules, water molecules which are coming in contact with the heating coil, they get heat in the form of conduction, and then they become, once they become heated, they become lighter because density decreases with increase in temperature. So, they become lighter and then they start moving upward. So, that portion cannot remain vacant. So, what is happening? Then some other fluid is coming and taking that positions which is of heavier or higher density. So, this way the circulation takes place, and this kind of circulation which is happening due to natural convection, this is called natural convection. Here we have not imparted any extra energy, extra force for the movement of the molecules other than the heat energy. Here I will show you some typical, consider a case of a plate. This is the wall, and here a fluid is flowing like this. Now, we know there is a velocity distribution. If you have studied in case of fluid mechanics, there will be a velocity distribution. So, here we will say that this here say V x infinity, and here I will say that temperature is T infinity, and so we see that velocity it changes along this direction. So, temperature is also changes along this direction. Here it is a T wall temperature, and the temperature T infinity is the free stream temperature. What is this free stream? Free stream condition is the condition when the effect of the wall is not experienced on the fluid element. That means, in this fluid element the velocity of the fluid element is not disturbed by the opposite effect or the shear force offered by the wall or the consecutive layers. At the same time, so the temperature also is not disturbed by the temperature of this. That means what? That between two successive layers, there is no more change in the velocity or the temperature of the fluid streams. These are called free or your free stream temperature and free stream velocity. That means, stream is free from the effect of the wall. Now, what happens? So, this is a typical velocity of the fluid along x direction. So, this is your x direction. Now, what happens in case of convective heat transfer? The heat transfer rate q dot x is given as h a T w minus T infinity. So, this is called Newton's law of cooling. As we have seen, in case of conduction, there is a Fourier's law of heat transfer. Here, the Newton's law of cooling, which discusses the basic convective heat transfer phenomena. Here, one thing also we can see that we can write this as T w minus T infinity by 1 by H A. So, this can be written as that equivalent to driving force by resistance. So, we can see here that the driving force is nothing but the temperature difference between the wall and the free stream, and the resistance is that 1 by H A, where A is the area of heat transfer. This is the surface area of the plate over which the flow is taking place, that is called area of heat transfer, and that H is called heat transfer coefficient. Convective also it is called convective heat transfer coefficient, because it characterizes the convective heat transport. Therefore, it is also called convective heat transfer coefficient. H is called convective and we can see that this convective heat transfer coefficient also is called, sometimes is called as film conductance. What does it mean? On the wall there will be a film of the liquid, and we know that is from the no slip conditions, when even if there is a flow of fluid over the plate, due to the no slip conditions, some of the fluid elements which will be sticking to the surface, which is adhering to the surface of the plate, they will not move, because the wall is not moving, surface is not moving. So, those fluid elements also will not move, that is called no slip conditions. So, some of the fluid elements will stick to the surface of this. So, this is called they are making kind of film kind of things, and the resistance offered by the film is also taken care of by the inverse of this convective heat transfer coefficient H, and therefore, the heat is being transferred or conducted. Basically, what is happening, those fluid elements which is adhered to the surface of the plane, the heat transfer is taking place in the form of conduction, and this happening through the film, and therefore, sometimes H is called film conductance. So, you can understand from the surface of the wall till the free stream condition, the heat is being transported by a combined mechanism. One is the very initial stage from the wall to the adjacent fluid layer by conduction, and then from conduction it is gradually switching over to the convection mode. So, these convection and conduction phenomena they take place in a combined way. However, H represents the overall mechanism of this heat transport, and therefore, H is called convective heat transfer coefficient, and 1 by H A is called the corresponding convective heat transfer resistance. And we can understand that depending upon, as because it is a phenomena that is happening because of these layers being associated with this, and it is between the layers the transport is taking place till the free stream conditions, we can understand that H should be a function of fluid, H should be function of flow conditions. So, that is why H is a flow property, H is a fluid property also. So, H varies, H is function of fluid property like viscosity, density, then specific heat, then thermal conductivity, and flow property like velocity. So, H is function of this. We will see in future that different correlations have come out to explain about that heat transfer coefficient, to find out the values of heat transfer coefficient. Now, one thing we can say that unit of H or convective heat transfer coefficient is expressed as watt per meter square per Kelvin. Now, we will come down. Next step is the radiation. Now, radiation it is more specifically we will tell it to be the thermal radiation is the electromagnetic radiation that is emitted by the body due to its temperature, and this is a mode of heat transfer which takes place without the help of any medium. Now, radiation heat transfer is effective when the emitting body is at very high temperature. In practical situation, heat transfer is associated with more than one of the three modes of heat transport. So, heat transfer, you consider a case of heat transfer in a furnace. What is happening? That from the flame to the inner wall of the furnace, that heat is being transported by radiation and convection. From the inner wall of the furnace till the outer of the wall of the furnace, the heat is being transferred with the help of conduction, and from the outer wall of the furnace to the ambient, the heat is transferred by the help of convection and radiation. Okay. So, that the heat transfer usually takes place in the form of convection, conduction and radiation, either they are individually present or they are present in combination. In case of radiation, like conduction and convection, there is a law that is given by Stephen-Boltzmann law. Stephen-Boltzmann law, which states law of thermal radiation, which states that Q by A is equal to Q dot is equal to sigma into T to the power 4. So, this is called sigma is called Stephen-Boltzmann constant, and the value is sigma is equal to, we know, 5.669 into 10 to the power minus 8. Now, if the radiation, actually the radiated heat transfer is basically the exchange between two bodies. If two bodies are of temperature T1 and T2, then the net exchange between two bodies is, say, Q dot net, and that is equal to sigma into T1 to the power 4 minus T2 to the power 4. And we can see that this net exchange become significantly or is significant or important when the temperature difference between the bodies are substantially high or substantially more, is significant. When the temperature difference is small, that time the radiation heat exchange is not that way important. And therefore, when we say talk about the radiation, we talk about the furnaces, we talk about the radiations of the furnaces, from the furnace, because the temperature of the atmosphere and temperature of the furnace, there is a big difference in temperature is there. Now, this radiation heat exchange between two bodies is, there are certain other aspects on which it depends. The examples are, one is called emissivity function. What does it mean? Say emissivity function, I say F epsilon. Emissivity function means that, like this relationship, the Stephen-Boltzmann relationship of thermal radiation is valid for black body. So, black body only follows this relationship. That means what? The black body means that it, whatever radiation comes on it, it absorbs everything, or whatever it absorbs all its energy. So, its emissivity is equal to 1, but in other bodies, like which are called gray bodies or any other bodies, the emissivity is not equal to 1, there is a specific values of the emissivity. So, this net exchange depends upon the emissivity function. Net exchange also depend upon there is a geometric factor which is called also view factor. So, net exchange between two bodies also depends upon a factor that is called view factor or a geometric factor, and therefore, the net exchange between any two bodies could be written as F epsilon emissivity factor function into geometric function into sigma into area into T1 to the power 4 minus T2 to the power 4. So, this is what is given by its a derivation derived from the Stephen Boltzmann law of thermal radiation. So, now, we have in this through this lecture we try to explain that what is heat transfer, what is the need of heat transfer, what is the course and how the heat transfer, the basic modes of heat transfer. So, basically we try to see the introduction of these, how conduction takes place, how convection takes place, how radiation takes place. In a brief way we try to explain the things. Now, we will with time we will enter into the course in the deeper in the depth of the course we will enter into this, and we will try to see that how the things happens. Now, whatever we have discussed, if we try to understand with the help of a few questions, let us think the very first question which comes to my mind. Now, can we find the differences of the functions by a leather jacket or a woolen cloth? In the winters we use woolen cloth or a leather jacket. Now, how they do perform? If you see that woolen cloth has got lot of pores, and in that air is entrapped, whereas in the leather jacket the pores are almost not there, almost nil. So, what happens when we are putting leather jacket, then that it is acting and that the leather jacket or foam jackets, there the thermal conductivity of this material of which the jacket is made is very poor, very low, and therefore, the most important resistance is the conductive resistance, that is important here, and therefore, it is becoming comfortable when that heat transfer by conduction is involved. That means, under winter season the heat that from our body cannot go to the atmosphere, or the heat cannot go to the atmosphere, and we feel comfortable. But what happens when you take woolen cloth? What happens? This air is entrapped into this. So, this air is also having a very poor thermal conductivity, and because of that air acts as a barrier for the heat transfer. It gives the resistances, and therefore, we feel comfortable. Now, the question comes, when there is a breeze, cold breeze is there, then which one will be more effective? Yes, definitely the leather jacket will be more effective. The reason is, when you have a flow of air, and that time because of the breeze it enters through the leather jacket, it cannot enter into our body. So, there is no convective heat transport as possible at all, because there is no pores. Whereas, in case of woolen jackets there are pores, or woolen sweaters or woolen clothes, there are pores through which air can enter into, and there can be a convective heat transport. So, during the cold breeze woolen jacket may not be that much desirable than the sweaters, leather jackets. Now, another second question that is very simple question is that, say if I ask you a simple calculation, say heat transfer coefficient of air at 20 degree centigrade is heat transfer coefficient of air at like H of air at 20 degree centigrade is 25 watt per meter square per Kelvin. Now, if I ask how is the convective heat transfer resistance per meter square area, convective how much will be the convective heat transfer resistance per unit area? So, very simple. Simply we know that total convective heat transfer resistance is H into 1 by HA, that is the convective heat transfer resistance. 1 by H A. Now, in this case A is equal to 1. So, it is basically 1 by H is the convective heat transfer resistance per when area is equal to 1 unity per meter square. So, this is nothing but 1 by 25 and that is equal to 0.04 degree Kelvin per watt. So, you can see that unit of heat transfer resistance is 0.04 Kelvin per watt, and so this is the value of the heat transfer resistance. Then another question, let us formulate another question. Say a rod of diameter 1 centimeter and length 1 meter is immersed in a liquid. The tube is maintained at 80 degrees centigrade. The rod is maintained at 80 degrees centigrade. What is the heat transfer area to heat the liquid by the rod? Very simple question. You have a rod of 1 centimeter diameter and length 1 meter. So, this is the rod, you can say this is the 1 centimeter diameter and this is the length is 1 meter. So, what is the area for heat transfer? It should be that heat is being transferred by this surface as well as these surfaces. So, we should say that it is the area is pi d into L plus 2 into pi d square by 4. This is this area of two ends, and you see that this value is becoming 0.1 pi plus 2 into phi into 1 centimeter means pi d L, d is equal to 1 centimeter is equal to 0.01 meter. So, this is 0.01 pi plus 2 into pi into 0.01 whole square by 4. So, you can say that it is 0.01 pi plus this is 2 0.00005 pi. So, now we can write that it is equal to 0.1005 pi, this much meter square. Now, interestingly, what I wanted to say here is that depending upon the L by D ratio, we have to see that whether we will take this end effects or not. Higher the L by D ratio, lower will be the or less significant will be the contribution of the surfaces. So, while we calculating the heat transfer area, many times we neglect the edges, surface area of the edges is because of that reason. I hope you have understood the heat transfer basic modes of heat transfer by conduction, convection and radiation. Maybe in the next class onwards we will discuss in depth about the conduction phenomena. Thank you.